I am Javed Ahmad, Department of Mathematics, Jamshedpur Women's College. This video is meant for honors students of semester 4, paper 10. Initially, I have told you students by mistake that this is comes within paper 9th. So students are advised to treat the ring theory and related topics in paper 10, and students are familiar from this paper. In this video, we are going to discuss characteristics of a ring, integral domain, field, etc. Now let us try to define characteristics of a ring. The characteristics of a ring is defined as the smallest positive integer n such that na is equal to 0 for all a belongs to R. If there exists no such positive integer, then ring R is said to be of characteristic 0. Therefore, ring R is of characteristic 0 if Na is not equal to 0 for all A belongs to R, where n is any least positive integer. Let us take an example. If I6 is a set containing 6 elements like 0, 1, 2, 3, 4, 5, then the ring I6 plus 6 cross 6, where plus 6 is addition modulo 6 and cross 6 means multiplication modulo 6, and students are familiar with the concept of addition modulo 6 and multiplication modulo 6 has the characteristic 6. For 6 multiplied by any element x is 0 for all x belongs to I6. Similarly, z plus dot is a ring of characteristic 0 because there exists no least positive integer such that n a is equal to 0 for all a belongs to z. Number 2, the characteristic of an integral domain R is either 0 or a positive integer n according as the order of unity element E of R is 0 or n, where E is regarded as an element of the additive group. Where E is regarded as an element of the additive group of R, that is n is the least positive integer such that ne is equal to 0. Number 3, an integral domain R plus dot is said to be ordered if it contains a subset R plus such that number 1, R plus is closed with respect to addition and multiplication as defined on R. That is, AB belongs to R plus. This implies A plus B belongs to R plus and AB belongs to R plus. This condition says that a system is said to be an integral domain R plus dot is said to be an ordered system if it contains a subset R plus of R which is closed with respect to the operation of addition and with respect to the operation of multiplication. And for the integral domain to be an ordered, its second condition is for any A belongs to R, one and only one of the following holds. Either A is equal to 0 or A belongs to R plus or minus A belongs to R plus. The elements of R plus are called positive elements of R. Also, the elements of R minus R plus are called negative elements of R. Example, the integral domain of integers is ordered. Why? Because it contains the subset n of all positive integers, which is closed with respect to addition and multiplication, and for any natural number a belongs to n, either a is 0, which is false, or a belongs to n, or minus a belongs to n. So out of these three conditions, as defined for an integral domain to be ordered is true here. So the integral domain of integers is ordered as it contains a subset n of natural numbers, that is n of all positive integers, which satisfies both the conditions for an integral domain to be ordered. But the integral domain of complex numbers is not ordered because it contains, this integral domain has not a subset of positive complex numbers, because there is no question of positive or negative complex numbers. Now we take a theorem. Theorem 1, prove that a ring R is without zero divisors if and only if the cancellation laws hold in R. Initially, we suppose that let R be a ring without zero divisors. Then we shall prove that the cancellation laws hold in R. Let AB belongs to R such that AB is equal to AC and A is not equal to 0. This implies A dot B minus C is equal to 0, where A is not equal to 0. This implies B minus C is equal to 0 as A is not equal to 0, and R has non-zero divisors. This implies B is equal to C. You have already seen in the definition of zero divisors that if AB is equal to 0, means either A is 0 or B is 0 or both is 0. Here A dot B minus C is equal to 0, but A is not 0, so B minus C is equal to 0. And this implies, thus AB is equal to AC, A is not equal to 0 implies B is equal to C. This shows that left cancellation law holds in R. Similarly, we can show that right cancellation law also holds in R if the ring R is without zero divisor. Conversely, suppose that R is a ring such that the cancellation laws hold in R, then we shall prove that the ring R has no zero divisors. Suppose if possible that R has zero divisors, then there exists AB belongs to R such that AB is equal to 0, where AB is not equal to 0. Now AB is equal to 0, A is not equal to 0. This implies AB is equal to A dot 0. This implies B is equal to 0 by left cancellation law, and we get a contradiction as C is not equal to 0. Similarly, AB is equal to 0, B is not equal to 0. This implies AB is equal to 0 dot B. This implies A is equal to 0 by right cancellation law. Again, we get a contradiction as A is not equal to 0, hence the result follows. Example 1, if R is a ring in which x square is equal to x for every x in R, prove that R is a commutative ring of characteristic 2. Proof. Let R be a ring such that x square is equal to x for all x belongs to R. Equation number 1. We have to prove that number 1, characteristic of R is 2, that is by definition 2x is equal to 0 For all x belongs to R, this implies x plus x is equal to 0. Condition result 2, we have to prove R is commutative, that is x dot y is equal to y dot x for all x y belongs to R. Proof of 1. We have x plus x whole square. We can write x plus x into x plus x and x into, by distributive law, this is simple, multiply this, you will get x square plus x square plus x square plus x square, and by given condition or by 1, x square is x, x square is x, x square is x, x square is x, and also x plus x square is equal to x plus x by 1. Hence x plus x is equal to x plus x plus x plus x. This implies x plus x plus 0. This is equal to this because the ring R has an additive identity. This implies 0 is equal to x plus x by left cancellation law for addition, and this proves the first condition. And number 2, let xy belongs to R. Then x plus y is equal to x plus y whole square by 1. This implies x plus y into x plus y, and as before x into x plus y into x plus y. This implies simply multiply, you get x square plus xy plus yx plus y square, and apply the condition 1. A given condition in the question, x square is equal to x, xy, yx, y, and this is x plus y plus xy plus yx. This implies x plus y plus 0 is equal to x plus y plus xy plus yx. This implies 0 is equal to xy plus yx, and indicate this by equation 2 by left cancellation law for addition. Let us take x into y is equal to x dash and yx is equal to y dash. Then x dash plus y dash is equal to 0 by 2. This implies x dash plus y dash is equal to 0 is equal to x dash plus x dash by case 1, because the characteristic of R is 2, and we have proved earlier x plus x is equal to 0. This implies y dash is equal to x dash by left cancellation law, and this implies yx is equal to xy, and this implies R is commutative, and hence the theorem is proved. Thank you.